that from pretty much the same point of view. And then later works after 2000. So after 2000, you will see that the sort of the citations of this Gurdjieff-Murdoch paper, it goes exponentially. So this is pretty much the idea, the underlying idea of surface elasticity theory. Now, if we want to look at an example, this is a very interesting example. So you take a cube, you apply a surface tension. Okay, surface tension means constant energy per unit area in the deformed volume, or in the deformed configuration. So now your structure wants to reduce its energy. So what it does is that for a given volume, you know that the sphere has the minimum surface. So what it does is that the cube transfers to a sphere. And that's exactly the reason that a droplet of water is generally spherical. Okay? So this is pretty much an interesting benchmark, and you can actually calculate your surface tension by this. We have done this. It's a very cool thing. But if you look at solids, now you talk about also different structure of the surface energy. So for fluid, surface tension is just one parameter. Let's call it gamma hat. For solids, you would have also some additional solid-like surface parameters. In order to calculate that, this is the experiment people do actually from atomistic calculation. You take this block, you apply periodic boundary conditions on these two sides, so it is sort of infinitely long. And then on top and the bottom, you break the bonds, okay? And you sort of apply a deformation to it, and look at the energy. For a certain thickness, you look at the energy, for instance, you are here, then you reduce the thickness, you come here, you reduce the thickness, you come here. So you keep reducing the thickness. That means that your solid, so your bulk energy is going to reduce by thickness, but your surface energy on the surface on top at the bottom, it's going to be constant, right? So sort of hypothetically, you could imagine if you come to the zero thickness, this little part which remains, this is your surface energy. So that's the way, or in this case, sort of double the surface energy because you have two surfaces. But clearly, you could never come to a zero thickness. You stop somewhere here at some nanometers or some angstroms, and then you go exponentially. So this is pretty much one approach to calculate those parameters. We have also heard about this heterogeneous material and homogenization. This is another thought about that. So if you have this material with heterogeneous microstructure like this one, what we do, say, if you have a nanoporous material, what we do is to add additional surface energy on the surface of these pores inside, okay? This is something different from what people do in the classical homogenization. Classical homogenization, you don't have this. So adding this, it actually gives you two very interesting effects. First, it gives you size dependence, which you generally want to have, and it gives you an additional shape dependence. It's not just the anisotropy effect and things like that. It's also the change of the area of this. And so I repeat again that the consideration of surface energy introduces a length scale into multi-scale problems. And please remember that classical first-order multi-scale methods do not contain any length scale. So we have since one way to add that additional length scale is to introduce higher gradients, for instance. But this one, again, I repeat, it's still a first-order multi-scale. It has additional surface energy, and it gives you already size effects. So it's a very simple example. I try to show this by this movie, if it works, yeah. So on the left, what I do, I have this, say, porous material. I apply a deformation to it. It's sort of a volumetric expansion. It's finite strain, and you have all the finite element implementation behind this. I'm not going into detail on that. So you would pretty much see this one. So it's what you classically get by homogenization, if you like. But now if you reduce the dimension of this, or say adding a surface energy to this, you see a slightly different behavior. So clearly we apply the same deformation, but now you see that the hole inside, it resists against deformation. Okay, so clearly this resistance against this deformation, it gives you sort of additional energy, right? The colors here, you don't have to worry about them. It's sort of the average stress to have a colorful picture. They don't mean anything special. So this looks like an academic example, but in fact, it's a bit more than that. If now you look at the same simulation, so you think that you have this material, you have this structure sort of repeated periodically, you can calculate the properties of the material by atomistic simulation, and you can compare it with this additional energy that we get from our surface modeling. So this is what we did. This size effect that you see generally with atomistic simulation, again, I repeat, it's not there in our classical first order continuum mechanics, but here we can pick it up easily. I should mention, this is not a curve fitting, okay? So this is the width of your RVE, if you like. So this is the width in, I think it's in nanometers or something. So this would be, no, it's the number of unit cells. So this is the number of unit cells. And this would be the stress. So this stress corresponds to the broken bonds. So what we do is that we just, sort of from atomistic calculation, you basically remove this hole, then you let it relax. Due to this relaxation, you introduce some stress to your material. And then from those stress induced in the material, you can calculate your surface material parameters, if you like. So again, I repeat, this is not a curve fitting. So what we did is basically to look only at this size, so 140. So for the size 140, we do all the calculations, we get the material parameters and everything. Then exactly with those parameters, I calculate this curve from continuum mechanics approach. These are a couple of, so like they are like 100 finite element simulation basically at different sizes. And clearly I can see this size effect. And then at the same time, I do different calculations for different sizes. Clearly you see that you have some deviation from these lines, but I think the agreement is quite impressive here. So it seems really, by adding the surface energy, you could capture atomistic simulation relatively easily. There is 2 points in these graphs which would be sort of introduction of my talk to higher gradients. First, you can see that I don't go higher than 200 unit cells in atomistic calculation. So the reason for that is computational time. Okay, so for my finite element calculations, I could go any size easily, but from computational time, this more than 200 unit cells is already taking more than a week, so I don't want to go there. But the more interesting is when you are at smaller size. So this is when you have like 40 unit cells. You see already a little deviation. If we want to go smaller than that, we may see even more deviation, but it's even more than just a deviation, because if you go smaller, you cannot really rely on your zero thickness assumption of the surface. So the whole theory becomes quite questionable, I think. And I think this would be sort of my view, why I need these higher gradients and what I do here. So I think after this relatively long motivation, I could get to the talk. What we have here is again this potato. It is in material configuration, in time zero at material configuration, shown by capital letters basically. It is deformed via a nonlinear deformation map phi to the spatial configuration at time t. And then phi hat is basically evaluation of the phi on the surface. So it's pretty much just a phi. And we have the linear map, so the gradients of the deformation gradient denoted as f, which sort of maps the volume elements from material configuration, or the line elements from material configuration to spatial configuration in the bulk. And the projection of that would be this f hat tangential. Okay, so f is the deformation gradient, f hat is the deformation gradient is on the surface, and then this f hat tangential is the projection of the deformation gradient to the surface. And then f hat normal is the remaining part basically. So in Francesco's talk, if you remember, this I hat tangential would be more like P, which was the projection, and I hat normal is more like a Q, which is the rest. So this is pretty much the whole story. And it's important if you just remember this picture. I try not to use many formulas, but just remember that the hat is a surface quantity, this parallel operator is a tangential thing, and this is the normal to the surface. So this is here the story. The classical surface elasticity theory allows the surface energy to depend only on the superficial surface deformation gradient. So this is sort of the Gurtin's assumption from starting with the surface elasticity theory. And the simulations I showed you, it's already with this assumption. Okay? So the energy depends only on this tangential part. But physics requires the surface energy to depend on total deformation gradients evaluated at the surface rather than its projection onto the surface. Okay? So what we want to do here is to allow the surface energy to depend not only just on the tangential part, but also on the normal part, okay? Or on the full surface deformation gradient. I try to explain why I say physics requires this by looking back a little to the literature and the observations. So again, remember what Gurtin and Murdoch did. They presented a surface elasticity theory based on an idea of a two-dimensional membrane bonded to the surface of the bulk submaterial. This is what they did, basically, in a nutshell. Later, Stagnant and Ogden, they looked more carefully into this model, and they realized that they still modeled the surface as a two-dimensional elastic continuum, but they generalized the work of Gurtin by incorporating elastic resistance to flexure at the film at the constitutive level. Okay, so what they did is pretty much like this. If you think now you have a zero thickness membrane, under tension everything is fine, but if you have compression, you have basically no resistance. So what you want to have is adding additional regularization against this expression compression mode, and they do it by adding a flexural resistance or the resistance against curvature, if you like. Later, in fact, this work is becoming more popular these days. I mean, later people like Elliot Fried, Pradeep Sharma, and Harold Park, they looked into basically nanowires, and they have done simulations, or they had already simulations with a little bit deviation at small sizes, and they realized actually adding this little contribution could give them much better results. So there is a good reason to have that additional contribution. This is kind of my favorite work here from Samuel Forest, Nicolas Cordero, and Esteban Busso. So the linear elastic isotropic first strain gradient theory is not sufficient close to the surface. A surface tension model would be inappropriate since at that size the capillary effect is not confined to an infinitesimal surface. So they call it capillary effect because they are looking into elastic fluids and Korteweg equations, but it's pretty much the same idea and philosophy behind it. At the end, we have also this additional thing. So what we did, and also I think we saw it in the talk by Victor Eremiev, if you look at the surface elastic parameters, you can basically calculate the admissible range for these parameters, and you realize that the admissible range for these parameters is not capable to capture that weakening effect. Okay, so it's not that always the smaller is stronger, sometimes the smaller is weaker, but then mathematically we could only capture the smaller, stronger effect. So this is the last thing, and I think that's kind of the motivation for getting finally to the higher gradients. So here is again the story. We look at the surface. Now you have two surfaces at the junction, and each surface has its own normal. So surface I, it has an n hat I, n is normal. Surface J, it has n hat J. Then we have also m hats. M hats are normal to the boundary of the surface, but they are tangential to the surface. So m hat I and m hat J are not parallel. And then, similar to the surface, we could talk about the junction of the surface, which would be curves. And we could talk about the junctions of the curves, which would be points. So we use hat for surface quantities and tilde for curve quantities. And I don't go into the details. It's just to remember that you should be very careful about this normal and tangentials, and if this normal in the sense of Frenet or normal to the surface, it's quite annoying to derive the equations actually. But so at the end of the day, you look into your equations back. So X spatial configuration is mapped from material configuration by phi. Now the formation gradient, we call it F1 here, is the gradient of that phi. The first gradient of that. The second gradient of that, we call it F2. So it's a very intuitive notation, although we fight it a lot about this notation. And the third gradient of phi is F3. Okay? Now on the surface, we do the same thing. F hat 1 would be the first gradient of the surface deformation map, and F hat 2 is the second gradient. The same thing, so F tilde would be the curve gradient of the deformation map. If you want to see now the hierarchy, I think this is nicely shown here. So if you have the first gradients on the curve, you need the second gradient on the surface and the third in the bulk. So if you want to have sort of deformation at points, then it means you need the second gradient on the curve, third gradient on the surface, fourth gradient in the bulk. This hierarchy is actually interesting to see. I just want to add one more thing. If you decompose the surface deformation gradient to the tangential and normal part, you could also do the first gradient for the curve, so you can also decompose it to the tangential and normal part. But if you look at the second gradient of the surface deformation gradient, so the second gradient, it has now 4 contributions. The first contribution is purely tangential, the last one is purely normal, and you see 2 mixed basically components. So, but the first one, which is purely tangential, still if you calculate it and if you write it down, you see this structure. So it has normal in it and it has also curvature in it. This is exactly the way this theory actually boils down to that Stagnant-Ogden theory. In fact, if you do the calculation, you would see that if you allow the bulk energy to be only depending on F1, so if you have a first order bulk material, you could only have a tangential part of the surface gradient. Okay? So you could only have F hat 1 tangential, and you could only have F hat 2 purely tangential. But still, this F hat 2 purely tangential, it has curvature in it and has normal in it. What we want to do is to look into these additional parts, to the normal parts. So it simplifies to Stagnant-Ogden theory, but it's more general. So now we just follow basically the Mindlin's idea. We have this total energy we want to minimize with respect to spatial variations. I split it into internal and external part. The internal part would be the bulk contribution, basically depending on the deformation gradients of different levels or different orders, and the surface part is the green part, the curve part is the red part. For going further, we do this assumption. This is geometrically nonlinear, so I'm using this P. It's like a polarized stress or generalized polarized stress, not Cauchy ones. So P1 would be the derivative of the bulk energy with respect to F1. P2 is the derivative of bulk energy with respect to F2. And like that, for the surface, we do the same thing. And then there's variations of the energy. It can be nicely written like that. So we use a lot of mathematics in between, which is basically just integration by parts and divergence theorems or extended divergence theorems, if you like, on the surface and the bulk and the curve. And this form could be written into this form. Okay? So I promised not to have many formulations, so I don't write the details. But the interesting thing is that you can see that so the variation of internal energy could be written as 9 integrals. Okay? So you can split it basically into 9 integrals. Now, we want to set the variation of total energy to 0. This is the next step of this recipe of Mindlin, basically. So you set up a external energy or external potential which fits to your internal one, and then you get sort of the proper boundary condition, if you like. Now, if you see at the first integral, this is an integral over the bulk, and this guy B1 is the energy conjugate to the displacement in the bulk, so it's basically your body forces. I use the P to denote it's prescribed. If you look at the same thing, so you see now something as a work conjugate to displacement on the surface, so it's traction, basically. It's the surface traction, then this one would be the curve traction. These are the point forces. Okay. The rest, I would call them just generalized tractions. They are integrals over the surface and over the curve, and they are work conjugates to normal gradients in different directions or second normal gradients. Okay, now I have to have this slide with many equations. If you remember, we had basically 9 types of integrals, okay? So that gives us 9 equations. And these 9 equations, the first one should be familiar to everybody. This is just the divergence of P minus divergence of, if you call P2 was the second pure stress, and the P3 was the third one. So this is pretty much what you have in the bulk for the third order continua. The second one is on the surface. It's difficult to see what's going on in details, but for instance, it's interesting to see that your P hat 1, which is your surface stress, is adding to P2, which is the second bulk, the second gradient bulk stress, and to the divergence of P3, which is the third gradient bulk stress. So if you look at this structure, it tells you a lot, and we have also defined this S hat operators, which is like a surface divergence of a projections of a surface quantity, to simplify the equations. But this is pretty much it. So if you simplify these equations, you get basically everything you want. And I just do a little simplification here to show you how it works. So we simplified the first for the case of first order continua without any surface or curve energy. Then I show how it boils down to the third order continua, which would be more like a mean-means work, but a geometrically nonlinear setting. And also finally the first order continua with surface elasticity theory. So if you remove all the additional terms, you end up with this one, which is clearly the balance of linear momentum and tractions on the boundary. You're familiar with it. For a third order continua without surface and curve energy, so this is basically mean-means work. And in fact, to reassure, I took this from the mean-means paper. You can see that it's basically this equation in different notations, and these three equations. Yeah, just I wanted to emphasize, you have seen we had 9 equations, but these are only 4, and Mindlin has also 4. The remaining 5, we were looking for it. It's actually in the appendix of the paper by Mindlin. So you can also see he did that too. And finally, the first order continua with surface energy and without curve energy, so it's more like Gurtin's idea, but a little extension. Do you want me to finish? Okay.
I am politely pressing you.
I see. So in summary, the results of Mindlin were generalized to the case of geometrically nonlinear deformable bodies with energetic surfaces and curves. Volume, surface, and curve energy cannot depend on deformation measures in arbitrary waves. And finally, maybe I just emphasize on this, that the classical first-order surface elasticity theory is generalized in the sense that the surface energy density depends on the total surface deformation. This requires a second-order bulk. Okay? It is clear that Gurtin-Murdoch surface elasticity theory is intrinsically limited since it is associated with the first-order continua in the bulk. And thank you very much for your attention.
This is a beautiful theory. I just want to bring to your attention we have a recent paper in John Anders, recently 2014.
Okay.
About annular against regions with transformative style.
Okay.
So this regions with a different material properties.
Okay.
And so they are like inclusions of finite techniques. Now, you can consider, so it is different material matrix. This cannot be solved by superposition of an SVD problem.
Sure.
Because the Green's function does not exist for finite. It is finite inclusion. So, this, if you consider the outer matrix to be absent, then it will be a surface layer. So this pillar against plane which corresponds to stresses of surface tension. But this is a three-dimensional. If you don't we take the small in addition to see. So we get the Gurtin-Murdoch theory in the but in addition, we have the other curve terms that account for the curvature and the relative thickness.
Okay.
Moreover, this theory concludes so this the SLB energy due to eigenstrain will be this surface energy. But we have also the driving forces on the surfaces. And these driving forces are the average stress on the boundary times the transformation strain. And since we have the thicker model, we can have the coupling of the driving force between a surface layer that has thickness. So the coupling of the driving force on the two surfaces is accounted for, and this coupling may make an interface unstable according to what are the elastic constants of the interface material and the bulk. So these are some additional models that
If you insist for jet lag, we'll have discussion about this at lunchtime.
Okay, the way I see surface theory, maybe if you agree, is that you start from assumptions of finite thickness and you have a limit procedure. And I guess that for this mental operation, the correct justification should be gamma reference. I mean,
it is identical. It leads to the same thing. Steigman showed it. He didn't publish it yet. Actually, we talked about that. Yes. I'm not an expert in gamma convergence, but I know David Steigman actually recently did it.
It's a very natural way.
Yeah.
I mean, dimensional reduction, family of function, and
Exactly.
thickness.
Yeah. Yeah, absolutely, I agree.